Hello, here's another couple of questions on astronomy and cosmology. So we start off, state the cosmological principle. Okay, there's three main bits I suppose we go for on this. So we can say the laws of physics apply at all time and space. Apply at all time and space. So this is essentially saying that we can conduct experiments, observations, things like that on Earth, and then apply that to the whole of the universe in order to construct theories. So, there's nothing particularly odd about the situation that we're currently in studying physics. This applies throughout the history, the future, and the space of the universe. So we've got that. We can say that the universe is homogeneous on the large scale. So this is getting at matter distribution. So even distribution of matter. And then we can say that it is isotropic. So the universe is isotropic also on the large scale. So on the large scale, so it looks the same in all directions. So there's no center or edge to the universe. Looks the same in all directions. Right. So it's not like we've got all galaxies are in one direction of the sky and none in the other directions. So yeah, three main parts. So these are our baseline assumptions for actually being able to conduct physics on Earth and then apply it to the universe. So it's an important set of assumptions. B, state some of the properties of the microwave background radiation observed from Earth. Discuss how the background microwave radiation is linked to the Big Bang model of the universe. Interesting that they've written microwave background radiation and then background microwave radiation in the same question. Not that it really matters, but yeah, just a bit odd. So yeah, some of the properties, again, we don't need many properties. So we can say, first of all, the intensity is the same in all directions. Now, some people get caught out by this, that they'll just say that the microwave background radiation is the same in all directions. They'll leave out the intensity bit. But the intensity bit is important because otherwise, what are you saying is the same in all directions if you leave out the intensity? I mean, is it the intensity? Is it the wavelength? It could be many different things. So say what it is that is the same in all directions. So we can say that, and we can say that the wavelength corresponds to a black body of temperature 2.7 Kelvin, which is important. So that's two properties. So that's some of the properties. That's two of them. I'm quite happy with those. Discuss then how this is then linked to the Big Bang model of the universe. So this temperature part of it is particularly important because then you can say that the Big Bang and subsequent expansion, so because it's the expansion part which is important for this, subsequent expansion led to cooling. So we're already saying some significant things. Okay, you might think these are obvious things about the Big Bang model, but you've got a Big Bang, an expansion and cooling. There's three things there: creation, expansion, cooling. So it said three things about the Big Bang model of the universe, even though they might be quite obvious things you might think. So that led to cooling. And then we can say, so high energy, these would be gamma ray photons. So gamma waves, or gamma photons, whatever you want to describe them as, have cooled to lower energy microwaves. And that is what is so important about the 2.7 Kelvin. So lower energy microwaves over the lifetime of the universe. Lifetime of universe. So yeah, so that is linking in two of these features of the microwave background radiation with the Big Bang model of the universe. So again, just be concise and clear in what you're saying. Get the key words in: creation, expansion, cooling, high energy to low energy, gamma wave to microwave. So yeah, it's quite a nice little descriptive question, that one. Question 5 they've got here, although the second one in this set. Calculate the distance of 1 light year in meters. So this is 3 times 10 to the 8 is our meters per second. And this is a light year, so we need to multiply by seconds in a year. So multiply by 60, so that's seconds in a minute, minutes in an hour, hours in a day, days in a year. So we multiply all of those things together and we end up with 9.48 times 10 to the 15. So 9.5 times 10 to the 15 meters to two significant figures. Right, so that was fine. That's just the definition. Figure 10.1 shows an incomplete diagram drawn by a student to show what is meant by a distance of 1 parsec. So 1 parallax arc second. Not to scale, yeah, clearly not. Complete this figure by showing the distances 1 parsec, 1 astronomical unit, and the parallax angle of 1 second of arc. Okay, so the parsec is the distance then from the sun to the star, which is essentially the same as the distance of the Earth from the star. I mean, it's the same thing. These angles are so small, but still, let's mark that on then. So this is our distance there, 1 parsec, or you could mark it, I suppose, on this dotted line here, 1 parsec. Then we got 1 astronomical unit, so that's distance from Earth to Sun. So that is our 1 astronomical unit. And then what was the other thing we have to mark on? Oh yeah, the angle. So that is going to be here. That is our 1 second of arc. So 1 double dash for seconds. There's a single dash for minutes and the circle for degrees. Okay, on some diagrams, they put the angle on the other side, but from basic geometry, we can see that that is the same angle. So that's marking those on. Next bit of the question. Recent supernova, SN 2011 FE, in the Pinwheel galaxy M101, released 10 to the 44 joules of energy, so a lot of energy. Supernova 2.1 times 10 to the 7 light years away. Calculate the distance of this supernova in parsecs. So if it's 2.1 times 10 to the 7 light years, then we need to multiply by the meters in a light year that we worked out, the 9.48, which is still on my calculator, times 10 to the 15. So that gives us the distance in meters. They've given us the distance here, meters in a parsec. So we divide by the 3.1 times 10 to the 16, and that is going to give us our parsecs, which is going to have to be a little bit lower, order of magnitude. Well, not an order, it's about what, a third. We're dropping it down by, was it 3.2 or something? When you divide, you convert from light years to parsecs, but still, let's see what the calculator tells us on this. 6.4 times 10 to the 6 parsecs, which is about what you'd expect. You know, you multiply that by 3 and a bit, and you're going to come out around about that. Next bit, our sun radiates energy at a rate of 4 times 10 to the 26 watts. Let's break the time in years it would take to release that amount of energy. Okay, so we've got 10 to the 44 joules. Divide that by joules per second. So divide that by 4 times 10 to the 26. That's going to give us seconds. We've got joules divided by joules per second. So that's going to be 2.5. And then we got 18 minus 1, so 10 to the minus 17 seconds. So we need to turn that into years. So we now need to divide by the number of seconds in a year, which, yeah, they've not got here. Okay, I'll do it all again. So 60 times 60 times 24 times 365 and a quarter, which is then coming out at 7.9 times 10 to the 9 years. Okay. One of the possible remnants of a supernova event is a black hole. State 2 properties of a black hole. So we just want 2 statements. We don't need anything particularly groundbreaking on this. So for the first one, we'll say it is a singularity, so a good keyword, of infinite density. So that's sort of belt and braces on that one. So singularity of infinite density. And then we can say that it's got a gravitational field which is strong enough that light cannot escape it. That light cannot escape from it. Light cannot escape from it. I mean, you could probably, I mean, there's other things you could say. You could say that they, I don't know, radiate Hawking radiation. That could be something else that you could say. You could talk about, I don't know, I mean, they all come back to the same thing, really, about their very high density and light can't get out. So, yeah, I mean, these two are the obvious ones to go to. That's why I didn't really give them that much thought coming in. But, yeah, that's fairly straightforward. I don't think you really need to. There's a massive list of simple properties that are going to be competing with these two, I wouldn't have thought. So, but maybe you've got other ones that come to mind. You know, it doesn't really matter too much what ones you pick, providing that they're ones that you've come across in the textbook or other sources. So, right, yeah, I'm just doing those two in this video, so it's quite a quick one, but it's some nice descriptive bits, particularly in the first question. And the descriptive ones often make people a little uncomfortable. So good to go through them.